Now there's something else called the convolution of f and g, and more than anything else this is useful when we want to do an inverse transform and we have the product of two transforms that we know. So if functions f and g are piecewise continuous on 0 to infinity, then the special product called the convolution of f and g, which is the function of t, is denoted f convoluted with g, is defined by this integral. F convoluted with g is equal to the integral from 0 to t, and that's tau going from 0 to t, of f of tau times g of t minus tau d tau. And you're thinking, ooh, why would that be interesting even a little bit? And the answer is not directly from this, but from what this leads to. And that's theorem 7.9 called the convolution theorem, see? Because if f and g of t are piecewise continuous and of exponential order, that means they have Laplace transforms, then the Laplace transform of the convolution of f and g is the product of the Laplace transforms of f of t and g of t. So in other words, it's f of s times g of s. That's going to be handiest, I think, maybe when we want to use an inverse transform for that. But let's go ahead and have a look at this. We'll do a couple problems, some backwards and some forwards.
I've had it up to here.
Oh, sorry.
I'm falling asleep now.
Well, I guess that's the way of it. So our first example, let's find the Laplace transform of this convolution, tau going from 0 to t of e to the tau times sine of t minus tau d tau. Tau's our variable here. So with our f of t equal to e to the t and our g of t equal to the sine of t, I think you can figure that out without too much difficulty, then this is the convolution of those functions. Hence, the Laplace transform of that convolution is the same as the Laplace transform of e of t times the Laplace transform of sine of t. Look how nice that was. Of course, we're going to wind up usually using this backwards, but that means this Laplace transform is just the Laplace transform of e to the t, which is 1 over s minus 1, times the Laplace transform of sine of t, which is 1 divided by s squared plus 1. So that is a Laplace transform of this convolution. So, like I say, it might be more useful in the backwards version. The inverse transform of f of s times g of s is the convolution of f and g, where f is the inverse transform of f of s and g is the inverse transform of g of s. That's assuming that they're piecewise continuous on 0 to infinity and of exponential order, otherwise they might not have Laplace transforms. So, as an example, find the inverse transform as a convolution, and here's what we're going to do. We're going to evaluate the inverse transform of 1 over s squared plus k squared squared. And we're not going to do partial fractions. We're just going to say that f of s and g of s are both 1 over s squared plus k squared, and that way we can get 1 over s squared plus k squared squared out of this. And then when we find the inverse transform, it's going to be the inverse transform of the product of those two things. And if we factor out a 1 over k squared and put a k in each numerator, so we can get sine of kt for this one, sine of kt for this one, then we got the convolution 1 over k squared times tau going from 0 to t of sine of k times tau times sine of k times t minus tau d tau. See, this is the convolution where this is the inverse transform of sine times the inverse transform of sine. So it's a convolution of those two functions. So now what do we do with that information? Well, let's harken back to pre-calculus. And you might recall cosine a plus b is cosine a cosine b minus sine a sine b, and cosine of a minus b is cosine a cosine b plus sine a sine b. I always tell my pre-calculus students, a cheer, cosine, cosine, sine, 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 or maybe cosine, cosine, secant, sine, sine. But with that in mind, then the cosine of a minus b minus the cosine of a plus b is the sine of a times the sine of b. And you're wondering, why would anyone go through that? Well, the object is to try to simplify this integral, which is pretty ugly. So if we let a equal k times tau and b equal k times t minus tau, and think about it like this, that's what we have in this integral that we want to do. So 1 over 2k, that's this 2 from the formula, times cosine of k times 2 tau minus t minus cosine of kt d tau, right? Think about it. We're replacing this sine a times sine of b, that's the a, that's the b, times cosine of a minus b, that's cosine of this minus this, right? And that's what that is. And then minus cosine of this plus this. Well, if we add those together, you can see that the k taus will cancel out, so we just get cosine of kt. So now we're getting to a doable integral. So 1 over 2 k squared, 0 to t, cosine of k times 2 tau minus t minus cosine of kt dt, or sorry, d tau. When we integrate this with respect to tau, we get integrating cosine, we get sine, except for the tau there, we got 2k times that tau, so it's 1 over 2k will be a factor in that antiderivative, and integrating this with respect to tau, believe it or not, is just tau times cosine of kt, because with respect to tau, this is just constant. But that will be going from 0 to t. So finally, when we put in 0 for tau, we get the negative sine of kt here, and negative tau times cosine of 0, which is just negative tau. So and anyway, then when we put in t, we get sine of k times 2t minus t, so that's just sine of k times t. And we put in t here, we get t times cosine of kt times an extra k, so I could factor out this k cubed, if you're wondering where that happened. Why did I get that extra k there? And that's why. So trust me that this yields this. You could use your software if you wanted to get there quickly. Sometimes I do that because I just need to do that. Yeah, I think I am too. So if the original problem would have been this, and then if we factored out the 1 over 2k cubed, I mean, the one we had wasn't that problem, it was this problem. But if we had a 2k cubed in the numerator, then we would have just derived this Laplace transform that's in most tables. The Laplace transform of sine of kt minus k times t times cosine of kt is 2k cubed over s squared plus k squared squared. Wow.
So very difficult.
It is kind of tough.